All right, ladies and gentlemen, so let's turn to page 15 of your notes. So what we're going to do today is expand upon a little bit. It's kind of a two-part lesson. Expand upon a little bit on where if you know one of your common Maclaurin polynomials, then you can find another Maclaurin polynomial by doing some operations, substituting. We're going to expand those operations into adding, subtracting, and multiplying as well. We also are going to talk about how you can actually differentiate and integrate a Taylor or Maclaurin polynomial as well. So again, we can differentiate a power series. You can take the derivative of either a Maclaurin series or Taylor series term by term. So in order to differentiate or integrate a Maclaurin or Taylor, you simply have to do it term by term. Again, so if you have a function represented by a power series it applies for either a Maclaurin or a Taylor, whether the center is at 0 or not. Then again, remember we have also, and it has a non-zero radius of convergence. That means you do have that middle of the road scenario. You do have this finite interval. Then one or two things can happen. The function is differentiable on this particular interval. So as long as there's an interval of convergence other than 0, then it is differentiable over that particular interval. If your series is differentiated term by term, then the resulting series has a radius of convergence and converges to f prime on the interval. So in other words, what this is saying is that the derivative will also have the same interval of convergence as the original Taylor or Maclaurin series. So this is really just important because you're talking about the differentiability of functions that are represented by the power series. According to the theorem, the power series for f has the same radius of convergence as the power series for f prime. So your original function and the derivative will have the same interval of convergence. And then if f prime is differentiable over this particular interval of convergence, the second derivative will also have the same interval of convergence as f and f prime, and for all your higher order derivatives as well. All right? So then if a function f can be represented by a power series with a non-zero radius of convergence, then f has derivative of all orders on your interval of convergence. So what we're going to do is we're going to actually prove, another way to prove why the derivative of sine x is by cosine x by using the Maclaurin, again because it's talking about Maclaurin, so I know the center is at 0, term by term. So again, I know that sine of x Maclaurin series, what does it start with again? What does sine start with? Sine starts with, does it start with 1 or x? X. Minus x to the third over 3 factorial plus x to the fifth over 5 factorial minus x to the seventh over 7 factorial plus dot 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 plus, remember what the general form for your sine of x looks like. That looks like your negative 1 to the k, x to the what is it, x to the 2k or x to the 2k plus 1? 2k plus 1 all over 2k plus 1 factorial. So then if I take the derivative of this particular Maclaurin series, I'm simply going to take it term by term. What's the derivative of x? The derivative of x is 1 minus. When I take the derivative of x to the third divided by 3 factorial, I know that's going to be a 3x squared over 3 factorial. Plus, when I take the derivative of x to the fifth over 5 factorial, that's going to be a 5x to the fourth over 5 factorial. Minus, when I take the derivative of x to the seventh over 7 factorial, that's going to be 7x to the sixth over 7 factorial. Plus, dot, 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 plus. Remember, I'm taking the derivative with respect to x, not k. So when I take the derivative of the nth term, again, negative 1 to the k is just a constant. So I'm going to have to apply my power rule when I take the derivative of x to the 2k plus 1. So that's going to give me a 2k plus 1 using my power rule times x. raised to the 2k, and when I subtract 1 from the power, 1 minus 1 will give me a 0. All over 2k plus 1 factorial. So any questions on how I differentiated this particular Maclaurin series? Now when I simplify this, I have 1. What is 3x squared divided by 3 factorial going to simplify down to? X squared over what? 2 factorial. Because I know 3 factorial is 3 times 2 times 1. So I know that 3 divided by 3 factorial will just simplify down to x squared over 2 factorial. Plus, what does 5x to the 4th divided by 5 factorial simplify down to? X to the 4th over 4 factorial. Because remember, 5 factorial is 5 times 4 times 3 times 2 times 1. So you can cancel out those 5s. Minus, what's 7x to the 6th divided by 7 factorial? Again, 7 factorial is 7 times 6 times 5 times 4 times 3 times 2 times 1. I think I missed one in there. But what's 7x to the 6th over 7 factorial going to simplify down to? X to the 6th over what? 6 factorial. Plus, dot, 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 plus. Now remember, 2k plus 1 factorial in the denominator. I can simplify this because I can rewrite 2k plus 1 factorial as 2k plus 1 times 2k factorial. So then I can cross out those 2k plus 1s. So notice I end up with a general term here of negative 1 to the k, x to the 2k, all over 2k factorial, which is, remember, equal to your cosine of x. So any questions on how I differentiated the sine of x Maclaurin term by term? Okay. So let's take a look at another one. I'm not going to make you prove where the inverse tangent of x Maclaurin polynomial comes from. If you really love doing Maclaurin polynomials, you can. But it gets to be pretty ugly because you have to do your quotient rule quite a bit. So inverse tangent of x Maclaurin polynomial is just like your sine of x, but it's without the factorials. So your inverse tangent of x Maclaurin is just like sine, but without the factorials. So your inverse tangent of x then, Maclaurin polynomial, is going to be x minus x to the 3rd over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus dot, 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 plus. You have your negative 1 to the k, x to the 2k plus 1, all over 2k plus 1. So then when I differentiate term by term, this is going to leave me with a 1 minus 3x squared divided by 3 plus 5x to the 4th over 5 minus 7x to the 6th over 7 plus your dot, 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 plus. I have my negative 1 to the k. Again, I'm going to end up with, using my power rule, 2k plus 1 raised to x to the 2k, all over 2k plus 1. And again, if you cross out your 2k plus 1, you're left with then, finally, when I simplify this, 1 minus x squared plus x to the 4th minus x to the 6th plus dot, 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 plus your negative 1 to the k, x to the 2k. And I'm going to show you a page in your textbook here that will give you all, and we're going to do the file folders next class. We're going to add a bunch of the Maclaurin polynomials that you'll want to memorize. This is actually your Maclaurin polynomial for 1 over 1 plus x squared. So there's a page in your textbook. Again, if you were to generate the Maclaurin polynomial by hand the long way, 1 over 1 plus x squared, this is what you'd end up with. All right? So any questions on how you can differentiate term by term? You can also integrate. You can integrate term by term as well. Again, if you have a power series, again, just like with derivatives, when you integrate, the interval of convergence will be the same for the antiderivative as well. So, for example, if your power representation of f is integrated, term by term, then the resulting series has a radius convergent r, and it converges for the antiderivative. So again, just like with the derivative, it'll have the same radius of convergence, an interval of convergence. So if alpha and beta are points on the interval, and if the power series of f is integrated term by term from alpha to beta, then the resulting series converges to r on the interval x minus r and x sub 0. Again, this applies for your Maclaurin and your Taylor as well. So you can prove why the integral of cosine of x is equal to sine of x plus c by integrating term by term. Again, we know what cosine of x Maclaurin is going to look like. Does it start with 1 or x? Does cosine start with 1 or x? Starts with n, 1. So then we know it goes minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial plus your dot 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 plus your negative 1 to the k x to the 2k all over 2k factorial. Again, this is your integral of cosine of x dx. So now I'm going to integrate term by term. What's your integral of 1? Your integral of 1 is just going to be a what? X. Minus. Integrate x squared. X squared is going to be x to the 3rd divided by 3 times 2 factorial. Plus. Integrate x to the 4th divided by 4 factorial. That's going to be an x to the 5th over 5 times 4 factorial. Minus x to the 7th over 7 times 6 factorial. Plus dot 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 plus, again, you're integrating with respect to x. That's going to be a negative 1 to the k. X to the 2k plus 1 divided by 2k plus 1 times 2k factorial plus your constant. So when I clean this up, what's another way to write 3 times 2 factorial in that denominator? That's going to be what? 3 factorial. Another way to write 5 times 4 factorial would be 5 factorial. Minus x to the 7th over 7 times 6 factorial I can write as a 7 factorial. Plus dot 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 plus negative 1 to the k, x to the 2k plus 1. All over, what's another way to write 2k plus 1 times 2k factorial? That's just simply going to be 2k plus 1 factorial plus c. So this is equal, as you can see, to your sine of x. I'm not hearing wow. Don't you think that's cool? I think it's the neatest thing. So you just proved why the derivative of sine is cosine, and then why the antiderivative of cosine is sine through your Maclaurin and Taylor Maclaurin polynomials. Isn't that neat? This is where those aha moments are supposed to come in. Where's my aha? Wow. You're thrilled, I can tell. But anyway, any questions, guys, on how you can integrate or how you can take the derivative of a Maclaurin series? So now, I want to move over to, we'll come back to part B. Let's take a look at, because this is what your homework's going to be about tonight, this example 3. So another way to find Taylor series is sometimes it's difficult or impossible to find the derivatives that are required to obtain a Taylor series. To resolve this problem, you can manipulate a function, in other words, manipulate a given Maclaurin or Taylor that you know, by doing some following operations. And you did some of this back in section 9.7, substitution. So if you saw sine of 2x, you know we could just replace the x with the 2x. We can also use differentiation. We can use integration. we could also use algebraic operations. We can add, multiply, divide. So we'll get into that next class where you actually will start adding, subtracting, multiplying, and dividing Taylor and Maclaurin polynomials together. So let's take a look at example 3. So a couple of things I want you to do. Find the first non-zero terms of the Maclaurin series for the function by making appropriate substitutions. Find the general term, and then state the radius of convergence. So that's why I said we'll do some more practice with radius of convergence here. So first of all, we know, again, we're looking for the first non-zero terms of the Maclaurin, so I know the center is where? The center is at 0. So I know what the Maclaurin series, hopefully by now, looks like for cosine of x. That's going to be 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial. Did I go out far enough? What did the directions say? 4. So did I go out far enough? No. Make sure you're reading those directions carefully. If they want 4, you better make sure you take it out to 4. And then my general term for cosine of x is, I know it's that negative 1 to the k, x to the 2k, all over 2k factorial. So now how do you think, now that I know what the Maclaurin for cosine of x looks like, how can I find the Maclaurin for cosine of 2x? What can I do? Substitute. What am I going to substitute? I'm going to substitute in 2x anywhere I see an x. So the cosine of 2x is going to be equal to 1 minus 2x to the second power over 2 factorial plus 2x raised to the 4th over 4 factorial minus 2x to the 6th over 6 factorial plus dot, 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 plus. You do the same substitution into the general term. So it'll be negative 1 to the k times 2x raised to the 2k all over 2k factorial. Right? So this is part A and B. So any questions on how I found the first 4 terms of your Maclaurin for cosine of 2x and then the general term? Now, for part C, they want me to state the radius of convergence of the series. So this goes back to what you did last night for homework. First of all, remember you're going to use your ratio test. You want to find the limit as k approaches infinity of the absolute value of u sub k plus 1 divided by u sub k. So I know u sub k, looking at my general term, it's the negative 1 to the k, 2x raised to the 2k, all over 2k factorial. My u sub k plus 1. Again, I know I'm going to do absolute value, so I don't even have to write this alternator up here. I could have done the absolute value. Is going to be 2x. Now be careful, it's 2 times k. So it's going to be 2 times k plus 1. Make sure you have that k plus 1 inside parentheses over there. Divided by 2 times parentheses k plus 1 factorial. So I can rewrite this numerator as the quantity of 2x raised to the 2k times 2x raised to the second power. So are we okay on how I wrote that? Over, again, I know this is going to be 2k plus 2 factorial. So I can rewrite this as a 2k plus 2 times 2k plus 1 times 2k factorial. So I'm kind of keeping an idea on my original to see what I'm going to eventually want to cancel out. So I know I'm going to want to break that factorial in the denominator down to a 2k factorial. So any questions on how I found the u sub k plus 1? So now I'm ready to go ahead and do my ratio test. So I'm going to find the limit as k goes to infinity. I'm going to take my u sub k plus 1, so that's my 2x, raised to the 2k, times 2x to the second power, all over 2k plus 2 times 2k plus 1 times 2k factorial. divide by u sub k, which means I'm going to multiply by the reciprocal of u sub k, so that's going to be my 2k factorial, divided by 2x raised to the 2k. So I can cross-cancel the 2k factorial. I can cross-cancel that 2x raised to the 2k. So I have the limit as k approaches infinity of 2x to the second power divided by 2k plus 2 times 2k plus 1. Remember, I only am concerning myself with the limit as k approaches infinity. So I'm going to pull out the absolute value of 2x to the second. So I have the absolute value of 2x to the second times the limit as k goes to infinity of 1 over 2k plus 2 times 2k plus 1. Boy, I took up this whole sheet, didn't I? So what's this limit going to be? 0. So 0 is less than 1. So then by my ratio test, what does it tell me about the radius of convergence? The radius of convergence is going to be what? All real numbers. So I know my radius of convergence then is going to be all real numbers. It's not asking me for anything else, but my radius of convergence is all real numbers. Well, if my radius, it's not asking me about it, my radius of convergence is all real numbers, what's the interval of convergence then going to be? All real numbers, negative infinity to infinity. All right? So any questions on the substitution? And you actually did that substitution back in the first section. I believe it was section 9.7 or beginning part of 9.8. All right, any questions on that? Let's take a look at part B. I'm going to get out a separate sheet of paper since I used almost that whole sheet on that problem there. So for part B, we have x squared times e to the x. Well, first of all, e to the x is a very common Maclaurin polynomial you should have memorized. Remember, e to the x is going to be your 1 plus x plus what? It's going to be your x squared over 2 factorial. Have I gone out far enough? No. How many terms am I taking it out? 4. So I have to take it out to plus x to the third over 3 factorial. Plus dot, 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 plus. Remember, it's x to the n over n factorial. You could do k, you could do n. So now, to come up with the Maclaurin polynomial for x squared times e to the x, that's where I mentioned you could perform not just substitution, but algebraic operations. So what I'm simply going to do is take the Maclaurin polynomial that I know for e to the x and multiply each term by x squared. So x squared times e to the x. So I'll multiply x squared times 1, which is just x squared, plus x times x squared is going to give me an x to the third. X squared times x squared over 2 factorial will give me an x to the fourth over 2 factorial. Plus x squared times x to the third is going to give me an x to the fifth. Oh, wait a minute. No. It's x squared raised to the third power over 3 factorial. Be careful about that. You're cubing x. You're replacing your... No, wait a minute. I was right the first time. X to the fifth over 3 factorial. Sorry about that. So did I do that right? Let's see. X squared, x to the third, x to the fourth, x to the fifth over 3 factorial. Plus, dot, 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 plus. I'm taking x squared, multiplying it by x to the n over n factorial. Is there another way I could write that numerator? X to the n plus 2. So another way I could write that general form is x to the 2 plus n all over n factorial. Okay? Any questions on how you can actually multiply to come up with another Maclaurin series? Again, if you want to use a k instead of an n, that's absolutely fine, but it doesn't matter. It's just a variable. Okay? So now you guys go ahead for me, and I want you guys to see if you can find the radius of convergence again. Here is my u sub n, or u sub k. So now go ahead and see if you can tell me what the radius of convergence would be for that particular series. Any of the work? Okay. So questions on how you can multiply. Again, a known Maclaurin to come up with another one. Let's take a look at another example. Let's take a look at, sometimes you have to do a combination of operations. You may have to do a substitution as well as a multiplication. So let's take a look at C. Here we have x times e to the negative x. So this is a combination of where not only are we going to do a substitution, but we're going to multiply by x as well. So again, we know that the Maclaurin series for e to the x, like we just saw, was 1 plus x squared over 2 factorial plus x to the third over 3 factorial plus dot 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 plus x to the k over k factorial. So do your substitution first. It doesn't really matter, but I like to do this. Go ahead and do the substitution first. So now to find e to the negative x, what I'm going to do is take x out and replace it with a negative x. So I'll have 1 plus negative x plus negative x to the second power over 2 factorial plus negative x to the third over 3 factorial plus dot 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 plus negative x to the k all over k factorial. So any questions on how I found the Maclaurin for e to the negative x? Now what's another way to write that general term? Notice what's going to happen with e to the negative x. By me replacing x with a negative x, this is going to become alternating, is it not? So I'm going to have 1 minus x plus x squared over 2 factorial minus x to the third over 3 factorial plus dot 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 plus. What's another way to show the alternator for this? Instead of writing negative x to the k, I can rewrite this as a negative 1 to the k times x to the k all over k factorial. So there's your e to the negative x. So any questions on how I found the Maclaurin series for e to the negative x? Now, to find the Maclaurin series for x times e to the negative x, I'm just simply going to multiply each term by x. So I'll have x minus x squared plus x to the third over 2 factorial minus x to the fourth over 3 factorial plus dot 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 plus negative 1 to the k, x to the k times x all over k factorial. What's another way to write this general form? Well, I can write this as negative 1 to the k, and how can I rewrite x to the k times x to the first? That would be what? X to the k plus 1 divided by k factorial. So any questions on that one? You guys go ahead now that we know what your general term is. Go ahead and find what that radius of convergence would be for that particular series. Came up with all real numbers again. Yep, I agree. So again, here's my work to show that we have that radius of convergence for all real numbers. All right. So any questions, guys, on, again, so sometimes you have to do more than one operation. You can do substitution, multiplication, or a combination of other operations as well. So you guys go ahead and try the next one for me. So we have sine of x squared. So again, starting with sine of x, see if you can find your Maclaurin series for sine of x squared. Now remember, this one you're not multiplying, you're actually going to be taking out the